Our goals for this lab are quite clear, and that's number one, we are looking to tell the difference between scientific thinking and everyday thinking. And the main idea here is that scientific thinking can be disproved. Right? So we don't prove anything. So there's a subset of that. There's an idea that follows the idea that we focus on disproving things. And they say we don't prove anything in science. There's no such thing as proving something. All we can do is disprove it. We'll talk more about this later. But the key today from this lab is that you understand that what we're trying to do is disprove things. The second important idea to get out of here is that we never know the truth in science. We don't know the truth. All we do is collect enough information to be certain or uncertain. So there's a level of certainty to some truth that we understand, some understanding. And all we really do is try to approach the truth. So we're trying to approach the truth. And by approaching the truth, what we're trying to do is come up with something that works. Something that works. It doesn't really matter to us if the truth is somewhat more nuanced, because the fact of the matter is, if it works, then it works, and if it doesn't, then we have to find another solution. If we disprove something, then it goes away. If we don't disprove it, it stays, and that's kind of the theme behind this scientific way of thinking. So you never know the truth. We're looking for what works. We're looking to approach the truth, and that goes back to what we had talked about before. That feeds into this idea of error, and so there's always this error that's surrounding every concept, every theory. It's an error that we accept this idea that error exists. And rather than just pretending error doesn't exist, we try to define it. We define it, we give it a number, we use it in our decisions as far as whether to apply this theory at this situation or not. And the reason is that if the error is too big for a particular scale or in a particular situation, then we need to reject using that theory for that situation, because the error it leaves too much to question. And we'll look at more detail of that next week. But for today, or for this lab, what we're really looking at again is these two main ideas: that we never know the truth, and that in science we're looking to disprove ideas. As long as you understand that, I think you'll be all right. Now, the details, those are the goals, but there's some details that you're going to need to know to be able to do well on the exam. And the quiz is on Monday. We will all right, so there's this idea that we never see things and that we never know the truth, right? And so for that reason we have rule number 1 for this lab. So don't open the lab, because just like we can't look inside an atom, we're not going to look inside this bag. And then we're going to try to use inductive reasoning, and there's a whole another little mini lecture I'm going to send you after this one. That's going to be another 10 minutes long. It's going to kind of go into what inductive and deductive reasoning are. It's just an intro and try to help you with figuring out how to do this lab. So in your observations, I mean, I think that's clear. I don't think everyone, based on my observations of you, I don't think anybody had a hard time making observations, right? So you're using your 5 senses to make observations and you're writing them down. That's not an issue for anybody, I don't think. And when you're coming up with your hypothesis, that tends to be a little more difficult. Then you have to think about something that's disprovable, right? You have to have an inference that's disprovable. Now, that disprovable inference tends to be written in an if-then statement. If this is true, then this is true. And all these observations, somehow they're connected. Somehow this one's connected to that one, that's connected to this one. There's some kind of pattern in these observations that you can find if you consider it. So what scientists do is what you did, and a lot of you were very frustrated because you looked at this bag, and you looked at it and you looked at it and you said, wait a minute, I don't know what to do with this bag. I have no idea what to do with this bag. What's inside this bag? I have no idea. Where do I even begin? Well, I have to tell you that when you look at DNA, you can look at any scientific truth over the last, since the days of the Egyptians. I can tell you that you can look at all these scientific theories, all the things that allow you to wear rubber synthetic shoes and have electricity come to your house and drive a car, fly a plane, all these technologies, all the science behind them. It took hundreds of years to just come up with one solution to try to figure out what's inside even just one of those mystery bags. So let's think about DNA. It took, depending on how far back you want to go in the concept, it probably took 100 years to come up with, with some idea about what DNA looks like and how it works. That mystery of DNA took probably close to 100 years to really define. And even today, more recently, we found that there's a whole nother level. There's actually a whole nother level of coding involved in DNA. And it's not really discovered this, but it's been well defined, I think accepted now, that we have this thing called epigenetics, where we had this concept from Watson and Crick in 1960s. It took 100 years to get there, right? The first question that we had was, what was the inheritable material? And then after many, many, many years of that, they discovered that people decided it was probably DNA, and then it was highly unlikely it was DNA, but they accepted it. And then Watson and Crick kind of described the process of coding, ATGC. But now we know that there's a whole nother level of epigenetics. So that from 1960 to now, there's a whole nother level of coding we call epigenetics. And we'll talk about it later. It's not important that you remember this particular example, but my point is that it took 100 years for us to even understand, to start to break down what DNA is, what it looks like. We still don't know what it looks like because we can't look at DNA. We could just look at some images of it after we shoot some X-rays at it, and where they bounce, they stimulate film, and we're able to look at a molecule that way. But we can't really just take your eyeball and look at DNA. And we really don't understand exactly how all the details of how it works yet. We're still working that out. I mean, we know a lot, and we obviously, since we can clone animals and we look at disease, and so we have a lot of knowledge that we're pretty sure is right. But nobody can tell you that they know the truth about how things work, because we're still working things out. And we're always going to be working things out. See, that's the point. We're always going to be working things out. There's always going to be something that is, less understood, or something that no one's looked at yet. And even if we've looked at it, there's something that we missed, or something that we have limited technology to look at, find enough detail. Well, in any case, let's get back on track. So we have this mystery bag, and you're trying to figure out what is disprovable and what is not, and you're trying to make a statement about that bag that's disprovable. A lot of you have tried to start with the question, what's inside this bag? Well, that may not be a great question. You might want to start off with, instead of trying to figure out what is inside the bag, try to figure out what is some of the properties of the stuff that's in the bag. What is this? Maybe a question you might ask is, what is not in the bag? Maybe that's a better question to ask. Right? That might make things a little easier. Or focus on a particular topic. Is a particular what is that? A particular topic is what is not in the bag. And then the next topic, the next question you might try to look at is what is the material metal? And what did I do when I asked this second question? I made the question simpler. I made the question more attainable. You see, what's inside the bag? God, it could be anything. But, some people have really good ideas. They think, well, it's definitely a little bead that you stick on things. It's definitely a little crown. It has the shape of a crown. I used to play with this as a kid. You're making assumptions. Those are all assumptions. Those are not scientific ways of thinking. You're not disproved. There's no way to disprove that. Because you're not allowed to open the bag. So there's no way to disprove that it's this little bead that you played with as a kid. Or any of the other some of the similar statements that I've heard and seen you guys speak and write down. So what you need to do is you need to ask yourself a simpler question, or try to say something that's not in a bag. So so let's say you want to see if it's metal. Is a material metal? Well, there's two things you can look at. You can look at how does it have is it magnetic? Right? Now, magnetism. Not all metals are strongly magnetic, so you might get a negative reading, a false negative. But if it is magnetic, you're pretty sure it is metal. So that's one test you can do. Another test you can do is conductivity. Does it conduct electricity? If it conducts electricity, then you're pretty sure it's a metal, right? So those are kind of things that you know. Those are things you know that you can do. Not too difficult, right? And so then you have to think of, okay, well, how would I write that up? Now, the example I gave you in class, I gave you a patently false statement, and I didn't want to give you real ideas like these. These came from students, not from me. This magnetic, there is something magnetic, and there's something conduct electricity. This came from students. These ideas from your colleagues. These are good ideas. So your hypothesis, though, has to be stated in such a way as to be disprovable. So you would probably write something like, if the magnet moves the object, then the object is magnetic. And that's a simple, just keep it simple. The simpler it is, the more likely it is for you to be able to get an answer that's satisfactory. The more complicated you make it, the more the bigger your plan, the more places there are for your plan to fall through. So your experimental design, you have to design things that you're going to keep constant. So the bag. So you're going to create and you're going to need a control group, by the way. We'll talk about what a control group is in a minute. So you're going to need the bag. You're probably going to keep the magnets, the type of magnets you use in your experiment. You're going to keep the same. You're probably going to keep the distance from the bag the same, right? So some distance that you're going to keep the bag before you do the two groups. And then you're probably going to keep what else? The amount of tape used on your control group the same as well. So what are your two groups? You have your experimental group, which is your unknown bag, right? So you have this unknown bag that you're going to test. And you have this other bag that you're going to create. You're actually going to create a bag. In this case, you're going to put little pieces of metal in it. So this is your positive control. But you're probably going to need a negative control too. So you're going to have this little bag here that's a negative control. In other words, a bag that doesn't have metal, so you put a little plastic in it or something. And then you're going to apply your your magnet to it, you're going to keep the distance from the magnet the same, right? You're going to keep that distance the same for all three of them. You're going to keep your maybe the speed. You're going to make these bags with the same amount of tape and the same bag material. So when you test it, you're going to be able to use these two groups, this positive control and this negative control, to compare to your experimental group or your unknown, right? So you're going to use these two groups, these control groups, to compare your data to. So when you know if this moves or not, you know it moves or not because it is metal or not metal, it is magnetic or not magnetic. It is not because there's some bag is interfering with it. Or how do you know the bag's not interfering with it? Because you use the same bag in the control groups, and the metal in your one control group moved, so you know that the paper is not interfering with the bag. And you know that there's not something that's not metal, that's magnetic by some odd reason that moves, even though maybe it's the magnet itself and not the magnetic force that moves it. Well, you will know that that's not true because you're going to use a magnet on something that is not metal, and it's probably not going to move. And when it doesn't move here, but it moves here, then that shows you that this process of using the magnet is correct. It works. So if then it moves in your unknown bag, you're pretty confident that it is magnetic. It's the bag, whatever's inside that bag is magnetic. Are you 100% sure? No, but you're pretty close. You're much closer to truth with control groups than you would be without control groups, and that's why control groups are so important. Okay, so your independent and dependent variable as far as the magnets are concerned, the magnetic. Now this is just an example. I say again, this is just an example. But if you're using magnets, then the distance from the bag is probably going to be your independent variable. So here you have this kind of plus and minus, and you have this bag. And is this distance you're gonna change it for every trial, and you're gonna see for all three bags how close you need to get before this material moves. And there'll be three groups. There'll be your positive control, your negative control, right, and your mystery bag, and you're gonna have distance here, and you can have I don't know, maybe a 10 millimeters, 11, 12, etc. And you're either going to get your positive control over here and negative control, and you're either going to get movement, no movement, and movement, or not. Something's going to happen. It's just an example, but there's movement here, but no movement here. This tells you that it's not something to do with the bag itself, that somehow using this particular material is moving the bag in some way that's not magnetic. And this tells you that the magnet does work through the bag. And this tells you that the stuff inside is magnetic. So each one of these tells you some different pieces of information. And so that would be your independent variable and your dependent variable. And again, your independent variable is your distance, and the dependent is whether it's going to move or not. So your movement of the material or not movement is your dependent, and whether the distance is your independent. You're going to collect the data. That data looks like this. There it is. There's your data table. Analyze the data. You're going to say if then. If the... Well, you already wrote the if then. I'm sorry. You're going to say to yourself, well, there was, movement in the positive control All right, that's one premise. One premise two. There was movement in the negative control. Right, there's your second one, and lastly, there was movement in the mystery bag. And the average, maybe you have an average, maybe you take an average of the distance, right? And the average distance for the movement of the positive control was 3 millimeters. There was no movement in the negative control, so that's NA, not applicable. And in the mystery bag, it was 2 millimeters. Let's say the average movement for the mystery bag in my trials was 10 millimeters. Okay, if that's true, then this is slightly less magnetic than the material that I'm using in the bag, but it is magnetic. And that would be my conclusion, right? Because this is true, and this is true, and this is true, my conclusion is true, which is the material inside the bag is magnetic. And there you have it. That's kind of the lab. And that's an example of it. I went through the whole process. I'm going to leave the what should you do next after you've completed that. I'll leave that for you for 20 extra credit points at the end of tomorrow. And then also this, I will send another video that's I've gone over my time, so I'm not going to do another second small one. I'm just going to send you this one. All right. Have a good day.